Welcome to Module 0, one of the Data Center Fire Protection Masterclass. This module introduces the data center fire protection ecosystem, and the central idea is simple. Protection is not a single device or system. It is an engineered, defense-in-depth architecture in which multiple barriers work together. We will follow the protection journey from prevention and detection, through control and suppression, to evacuation and recovery. The most important concept is coordination. Detection must communicate with command functions. Fire-water systems must support the required suppression strategy, and special hazards must be addressed within the overall design rather than in isolation. Throughout the module, we will also connect technical decisions to standards, the project design basis, and lifecycle assurance. That means requirements must be verified against the adopted code edition and confirmed through the applicable authority having jurisdiction, including DAMCR approval where relevant. The goal is more than installation. It is a traceable system of evidence showing that every barrier is designed, commissioned, maintained, and ready to perform when needed. This module provides a complete orientation to the data center fire protection ecosystem, from hazard prevention and early detection through suppression, recovery, and evidence governance. The goal is to establish a common technical language for owners, operators, designers, commissioning teams, specialist contractors, insurers, and AHJ or DAMCR reviewers. The suggested format is a 110-minute instructor-led session, followed by a 25-minute workshop and a 10-minute knowledge check. That timing can be adapted to the project's maturity and the audience's needs. Participants will develop practical outputs, including a protected space register, a system boundary map, a preliminary standards matrix, and a fire scenario and evidence owner register. By the end, I want participants to distinguish life safety, property loss, business continuity, and responder safety objectives. We'll connect room hazards to detection, suppression, notification, passive protection, and operational controls. We'll also clarify command authority, cause and effect, fail-safe states, reset authority, and local autonomy. Finally, we'll apply the hierarchy from law and AHJ requirements through adopted SNI, NFPA, and I codes, insurer criteria, infrastructure frameworks, and owner risk policy, while defining the evidence, IDM, impairment, and management of change controls that keep the system reliable. This module is organized around 4 learning blocks, all connected by 5 rules. Scenario-first design, defense in-depth, deterministic logic, authority hierarchy, and lifecycle evidence. Together, these rules provide a practical way to think about fire protection in data centers, where the consequences of an incident can extend well beyond the room where it begins. Block A establishes the performance objectives and risk model. We'll look at why data centers are different, how fire scenarios develop, and how consequence pathways and barrier logic shape the design. Block B focuses on protected spaces and layers of defense, including room taxonomy, risk ranking, passive protection, prevention, and human factors. Block C moves into the detection, control, and suppression architecture, covering ASD and VESDA, fire alarm and voice systems, cause and effect logic, and suppression options such as water, clean agent, brigade response, and special hazards. Finally, Block D addresses standards, assurance, commissioning, impairment management, and audit-ready evidence. We'll close with an incipient cable fault scenario, a protected space workshop, and a knowledge check. The goal is a defensible system, from initial risk to lifecycle evidence. This section establishes the foundation for the fire protection system, clear performance objectives, and a realistic risk model. The first step is to define what must be protected, because not every objective is the same. Life safety comes first, with a focus on safe evacuation and reliable access for responders. Asset protection is related, but distinct. Its purpose is to limit fire growth and reduce damage to equipment. Service continuity goes further, asking whether the event can be contained and whether recovery can proceed predictably. The second principle is to model credible fire scenarios, rather than relying on generic labels such as server room or electrical room. The actual scenario determines how fire may develop and which systems are exposed. Finally, barrier logic helps us test the protection strategy. We identify the barriers that must act before service loss becomes unacceptable, then look for single points of failure. In other words, the goal is not simply to install protection, but to understand how each layer contributes, and what happens if one layer does not perform as intended. A defensible data center fire protection strategy begins by defining the objective for each protected space, the consequence that is acceptable, and the evidence that demonstrates performance. The goal is not simply to install fire protection, but to make each decision traceable and supportable. The first objective is life safety. Detect and notify occupants, maintain tenable egress, and support firefighter access. Second is property protection, which means controlling fire growth, limiting smoke and liquid contamination, and protecting critical equipment. Third is service continuity. The strategy should prevent avoidable shutdowns, preserve redundant capacity, and provide controlled recovery paths. The remaining objectives broaden the risk picture. Responder safety requires clear access, isolation information, hazardous energy control, and a reliable water supply. Environmental control addresses fuel, extinguishing discharge, contaminated runoff, and battery decomposition products. Finally, evidence and governance require proof of the as-left configuration, test results, impairment control, and lifecycle readiness. The key design question is straightforward. Which objective controls each decision, and what residual risk has the owner formally accepted? This section explains why data centers need a fire strategy designed specifically around their operating environment. The risk is not limited to flame spread. Smoke contamination, liquid release, forced airflow, and dependence on continuous power can turn a relatively small incident into a major service interruption. The key principle is that detection and protection must follow the way the facility actually operates. High cooling airflow can dilute smoke and carry it away from ceiling detectors, so detection needs to account for airflow paths. Energized equipment may continue arcing or overheating until power is safely isolated and reignition remains possible. Combustible cable jackets, temporary cabling, and stored materials can support concealed fire growth. Liquids, including chilled water, direct-to-chip cooling fluids, and firefighting water, can damage electrical and information technology assets. We also need to consider batteries and fuel, including thermal runaway, gas, spills, and spray fires. Finally, HVAC, power, networking, and control systems are interdependent, meaning a small fire can become a large availability event. FMDS 5-32 identifies these exposures as principal concerns. This section frames fire protection around credible scenarios, rather than relying on room names alone. I start with the initiating events. Overheating at a rack PDU or cable connection, faults in busways, switchgear, or transformers, a UPS or battery thermal event, generator fuel release, hot work, and ignition involving HVAC equipment. These are the conditions that can begin the event. From there, the analysis follows the top event, uncontrolled fire or smoke in a critical space. The consequences may extend well beyond the point of ignition, including smoke contamination across multiple aisles, loss of cooling, cascading IT shutdown, suppression discharge or water migration, loss of a redundant power path, and fire spread to adjacent critical rooms. Ultimately, the impact can include an extended outage, cleanup, and recertification. The strategy therefore combines preventive barriers, such as electrical maintenance, thermography, separation, housekeeping, hot work controls, and early detection, with mitigative barriers, including alarms, response procedures, suppression, power and fuel isolation, and recovery planning. A scenario is acceptable only when its barriers, failure modes, responsible owner, and proof test are explicit. This section focuses on protected spaces and defense in depth, translating the overall scenario model into practical, room-by-room protection layers. The key idea is that every space should be treated as a distinct hazard and business interruption zone, rather than applying one identical solution across the facility. The labels at the bottom illustrate that approach. The data hall uses ASD, or air sampling detection, while electrical areas use IG, indicating an inert gas approach. Generators are associated with mist protection and common areas with hydrant coverage. These examples show how protection is matched to the room, its equipment, and its consequences. The second principle is layering. Passive boundaries, active suppression or detection systems, and operational controls should reinforce one another, so that a weakness in one layer does not become a total loss of protection. Finally, protection has to remain effective during maintenance and system changes. Availability is not just a design goal. It must be preserved through clear operational ownership, controlled work practices, and coordination whenever systems are isolated, modified, or returned to service. This worked example shows how a verified input register creates an auditable engineering basis for downstream decisions. The key principle is that every major design choice should trace back to a defined, reviewable input. The conceptual floor plate is 3,000 square meters, based on a 60 by 50 meter layout. The project includes 10 floors, with an overall height of 70 meters, and a 7-meter floor-to-floor dimension that includes services. The IT strategy targets concurrent maintainability, so the topology, maintenance paths, and operating procedures must demonstrate that the target can actually be achieved. For fire protection, the basis is wet risers combined with zone preaction branches. All risers remain wet, while preaction valves isolate only the horizontal IT branches. That distinction is important because it preserves the intended system behavior while supporting maintainability. Finally, the governing decision is clear. Adopting higher reliability measures does not replace the Fire and Life Safety Code or the authority having jurisdiction. The design remains governed by the Project Availability Target, NFPA 75:2024, NFPA 13:2025, the adopted code, and AHJ or DAMCR approval. This slide establishes the engineering basis for the fire protection design. The central idea is that a change in the hazard basis does not stay isolated. It propagates through a connected decision chain, from how the room is used, to how the hazard is classified, to the sprinkler demand, and ultimately to the pump, tank, and test criteria. The room name alone is not the classification. For a data hall, I need to review the actual fuel and commodity, the arrangement, and the approved risk basis. That means looking at the room inventory and the materials or equipment present, rather than assuming that every data hall belongs in ordinary hazard group 2. From there, the selected criteria determine the required density and area, or an applicable listed design approach. That drives the hydraulic demand, which then informs stored water volume and pump selection. Finally, the test criteria must confirm that the system performs as intended. So, the practical takeaway is simple. One hazard basis change can affect every downstream engineering decision. The governing references shown here are NFPA 13, including occupancy classification and the relevant design chapter, along with FM guidance documents DS5 to 32 and DS3 to 26. This slide establishes a protected space taxonomy for selecting fire protection based on the actual conditions in each space, rather than applying one solution everywhere. The assessment should consider the hazard, airflow, enclosure, occupancy, criticality, and interface conditions. Data halls require attention to high airflow, racks, busways, cable trays, and liquid cooling, with layers such as early detection, sprinklers or preaction, compartmentation, and controlled shutdown. MMR, ER, and NER spaces add dense fiber and carrier equipment, so detection, approved suppression, and access governance become especially important. UPS and battery rooms introduce power electronics, battery gases, ventilation, isolation, and propagation control. Electrical rooms, generators, fuel systems, fire water infrastructure, support areas, and external site hazards each have different scenarios and controls, from arc faults and hot surfaces to fuel spills, pump reliability, egress, and brigade access. The key administrative tool is the required space register. It should capture the space function, hazard, fire scenario, protection layers, interfaces, isolation authority, inspection and testing owner, and evidence location. That register connects design intent to ongoing governance and maintenance. This slide presents an illustrative, room-by-room risk heat map for a data center fire protection system. The key point is that risk is multidimensional. The matrix evaluates each protected space across ignition likelihood, fire growth potential, smoke sensitivity, water or liquid sensitivity, business interruption, and responder complexity. A room can have relatively modest fire growth potential, yet an extreme consequence if an incident interrupts critical operations. The rows cover spaces including the data hall, MMR, ER and NER rooms, UPS and VRLA areas, lithium energy storage, switchgear, generators, fuel storage, and fire pump facilities. The ratings range from low to very high, using the abbreviations shown at the bottom. For example, the data hall is rated very high for interruption consequence, while lithium ESS and several electrical areas show very high ratings in multiple categories. These ratings are illustrative, not a substitute for engineering judgment. We should use a site-specific hazard analysis to validate them, then apply the results to scenario analysis, resilience decisions, commissioning depth, and emergency response planning. This slide presents a defense in-depth architecture for protecting critical IT services in a data center fire scenario. The central idea is that no single technology can protect people, equipment, and operational continuity on its own. Reliability comes from independent, coordinated layers, each with a defined response if another layer fails. The sequence begins with prevention, including electrical maintenance, housekeeping, hot work controls, and management of fuels and batteries. If an incident still develops, containment limits its spread through compartmentation, fire stopping, separation, and control of cables and liquids. Detection then combines air sampling or high-sensitivity smoke detection with heat, flame, and off-gas monitoring, along with supervision of valves, flow, and pressure. Next, the system decides and notifies. The Fire Alarm Control Panel, releasing logic, communications, priorities, verification, and timers coordinate the response. Control and suppression may then act on power, fuel, and HVAC systems, while deploying water or agent systems. Finally, recovery requires safe isolation, controlled reentry, recommissioning, inspection, testing, and maintenance with evidence preserved. The design rule is simple. Every critical objective needs prevention, detection and decision, mitigation, and recovery paths. This section focuses on passive protection, compartmentation, and fire stopping, the measures that limit fire, smoke, liquid, and common mode failure before active systems can respond. The central idea is containment. A local event should remain local, rather than spreading from the data hall into the power room or across critical spaces. Compartmentation relies on rated walls and floors, protected openings, and adequate spatial separation. Penetration control is equally important. Every cable, busway, duct, and pipe that passes through a barrier needs an approved fire stop system, a documented installation record, and inspection whenever changes are made. Fire-rated doors must also close and latch reliably. The strategy extends beyond fire alone. Liquid migration needs a defined control and drainage approach, while combustible cable and storage materials should be limited. Tray, containment, and ceiling obstructions must be managed so they do not interfere with smoke movement or sprinkler discharge. Finally, this protection has to remain effective throughout the facility's life. Fire doors, dampers, fire stops, and barriers need to stay traceable after fit-out, additions, moves, changes, and maintenance. This section focuses on ignition prevention and the human element controls that keep small issues from becoming serious events. Many incidents begin during maintenance, temporary work, storage, or an unresolved equipment defect, rather than from a deficiency in the original design. The central principle is that no change is minor until its fire impact has been assessed and formally closed through management of change. Electrical reliability depends on thermography, connection and torque checks, breaker and relay testing, cable and bus inspection, and alarm trend review. For hot work, controls include permits, isolation, combustible clearance, a dedicated fire watch, post-work monitoring, and management of any temporary detector impairment. Good housekeeping means removing spare cable and carton accumulation, controlling staging, preserving sprinkler and detector access, and keeping underfloor and ceiling voids clean. Fuel and battery operations also require leak checks, supervised transfers, ventilation, chemistry records, off-gas response, and adherence to manufacturer limits. Finally, every addition, relocation, or modification should be reviewed for impacts on airflow, detection, sprinkler coverage, enclosure integrity, and control logic. Contractors need induction, permits, escalation routes, access control, response preplans, drills, and documented closeout. This slide presents a whole system view of data center fire protection. The central idea is that protection is not a single device or trade. It is a coordinated ecosystem that connects prevention, detection, decision-making, notification, suppression, and recovery. The key is coordination across the entire protection sequence. At the center, the coordinated fire protection model links the data hall, electrical and UPS spaces, generators and fuel areas, and common areas. Each environment has a representative strategy: ASD with preaction for the data hall, ASD with IG 541 or IG 100 for electrical and UPS spaces, flame detection with water mist for generator and fuel areas, and sprinkler with hydrant protection in common areas. The ecosystem also includes the FACP or FCC, ASD or VESDA, fire, water, and special hazard systems. These must connect with BMS and EPMS, IDM activities, and operator response. Finally, the design has to be validated through room strategy, listings, hydraulic or agent calculations, cause and effect, AHJ approval, and as-built evidence for the actual project. This section focuses on the detection, control, and suppression architecture that brings the fire protection system together as one deterministic response. The goal is to connect the inputs, decision logic, command authority, water and agent systems, brigade interfaces, and special hazard controls so each stage has a clear role and a predictable outcome. There are 3 principles to keep in mind. First, detection should follow airflow and the actual hazard, rather than simply reflecting what is easiest to install. Second, every input needs a defined output, priority, and reset authority. That clarity helps prevent ambiguity when multiple signals arrive or when the system needs to be restored. Third, suppression selection has to balance speed and reliability with complexity and consequence. The fastest option is not automatically the best option if it introduces unnecessary risk or operational burden. The architecture shown here moves from VESDA detection and its power supply through the fire alarm control or fire command center, into the releasing panel, and finally to the preaction and nitrogen systems. Each connection should support a deliberate, traceable response from detection through suppression. This section focuses on the detection ecosystem and how each signal should be classified. The key principle is to select sensors based on the fire signature, airflow, response objective, environment, and the action that follows the signal. 4 high airflow data halls, return air paths, underfloor spaces, or rack sampling ASD or HSSD systems, such as VESDA-E, are designed to identify incipient smoke early. Spot smoke detectors provide general coverage and confirmation, with spacing adjusted for airflow and listing. Heat or linear heat detection is better suited to hot equipment, cable routes, generators, or areas where smoke detection is impractical. Flame detection supports rapid response to open fuel spray or generator hazards, but requires careful line of sight and false source analysis. Off-gas or gas detection can monitor battery thermal events or hydrogen, with thresholds coordinated with ventilation and response procedures. Supervisory and process signals include water flow, tamper, low air, pressure, pump, leak, fuel, and local equipment alarms. Signal classes must remain explicit: alarm, supervisory, trouble, pre-alarm or early warning, release or discharge, and security or panic, which follows a separate workflow. This slide focuses on designing aspirating smoke detection, or ASD, and high-sensitivity smoke detection, or HSSD, for data halls with significant airflow. The central principle is that sampling architecture must follow the actual movement of air, from cold supply air at the rack inlets, through the racks, and into the hot return air path and sealing plenum. The design has to be proven, not simply drawn. That proof includes airflow studies, defined sampling zones, hole sizing, detector range, alarm thresholds, and practical maintenance access. The slide also identifies an FMDS 5 to 32 benchmark for conditions of at least 1.5 meters per second or 60 air changes per hour. In that situation, a very early warning fire detector pre-alarm is intended to reduce airflow below 1.5 meters per second, and the interlock must be acceptance tested. Performance testing then verifies remote port transport time of no more than 60 seconds, along with smoke movement, stratification, obstructions, and detector settings. Finally, operations should trend airflow and recurring early warnings, while contamination is isolated, cleaned, and documented. This slide provides a visual reference for an integrated data center fire protection architecture. It is organized as a simple flow from field input to durable evidence. At the input level, ASD or VESDA supplies early warning, while the fire alarm control or command center receives and manages the system signals. Those inputs move through listed logic, where the approved cause and effect strategy determines what happens next. The outputs are shown in parallel. Water protection is represented by the fire pump, including pump start and status. Agent protection is represented by IG 541 or IG 100 release and discharge. Voice functions are handled through PAVA or evacs for notification and evacuation messaging. Together, these paths support early warning, alarm, suppression, release control, and event recording. The important qualification is that this is representative architecture only. The actual installation is governed by the approved point list, network survivability requirements, command boundary, and cause and effect matrix. In other words, the diagram explains the relationship between detection, logic, actions, confirmation, and records, but it does not replace the project's approved design documentation. This section defines how the fire alarm, fire command center, and notification authority work together. The key principle is the listed fire safety system remains the source of truth. Field inputs, including smoke, heat, or flame detection, manual call points, water flow and tamper switches, pumps, and releasing panels, are received by the local fire alarm or releasing control system. That local system maintains addressable loops, power and battery supervision, priorities, timers, and critical autonomy. The Fire Command Center then provides site-wide enunciation, event chronology, operator guidance, and the information needed by the responding brigade. Notification and control functions may include voice evacuation, strobes, doors and lifts, HVAC, pumps, suppression, and fuel or power actions. Monitoring platforms such as BMS, EPMS, DCM, SOC or NOC systems, remote alarm services, and evidence archives receive approved status and commands. They do not replace the authoritative fire system. Critical functions must continue through network, HMI, or server loss. Fire and evacuation priorities override routine paging, and reset requires a named role, field verification, and an approved restoration sequence. Every alarm label must identify the exact asset, location, signal class, response, and escalation owner. This section focuses on cause and effect logic and on making every response deterministic rather than improvised. For each input, we need to define the priority, the verification or confirmation rule, the required outputs, the fail-safe state, bypass controls, reset authority, and the evidence that will be recorded. The essential principle is that every event must lead to a controlled, documented response. The sequence moves from the input event through verification and decision logic to output actions, operator response, and recovery evidence. An ASD alert may trigger notification and investigation, but not automatic suppression release unless approved. A pre-alarm escalates the response and prepares isolation. Confirmed fire or manual call point operation can initiate alarm notification, building system actions, brigade response, and the approved HVAC mode. Preaction or water flow events require alarm enunciation, pump response, and zone management. Clean agent release depends on coincident detection, warning, delay, discharge, and controlled reentry. Battery thermal events require ventilation, emergency response, and monitoring for escalation. These are examples only. The approved fire strategy, system listings, local code, and integrated risk assessment determine the final matrix. This section compares 4 water-based suppression strategies for data centers. The central issue is not simply whether a system uses water, but how quickly water can reach the hazard, how complex the system is to maintain, and what the consequences would be if water were admitted accidentally. Wet pipe is the fastest and simplest option, because the piping is already filled with water. It has low complexity and the greatest immediate readiness. Non-interlocked preaction is also fast, admitting water when detection or sprinkler operation occurs, and it reduces the empty pipe delay associated with more restrictive arrangements. Single interlock preaction adds another layer. Detection opens the valve, but sprinkler heat operation is still required before discharge. That makes response moderate and complexity high. Double interlock is the slowest and most complex. It requires both detection and a low air or sprinkler condition before water enters the piping. The slide identifies double interlock as an FMDS 5 to 32 property protection preference, but engineering caution is important. Its added fill delay, trim complexity, and maintenance burden should be accepted only when the approved risk strategy justifies that trade-off. This slide focuses on the complete operating chain of a preaction fire protection system, not just the valve itself. Water is held back at the supervised control valve and preaction valve set, while the downstream pipe network is supervised with air or nitrogen. In a double interlock arrangement, the releasing control must receive the required detection signal and confirm sprinkler side pressure loss before the valve opens. The releasing logic may include coincidence, a timer, and a disable control. This is different from a single interlock system, where detection alone opens the valve and sprinkler operation then produces discharge. Reliability depends on every link in that chain. Supervised points include valve tamper, low air or pressure, water flow and trip status, panel trouble or power loss, and compressor or nitrogen faults. Acceptance evidence should demonstrate the full sequence. Trim inspection, low air alarm, detection release, valve trip, water flow, drain or test connection, reset and restoration, FACP or BMS enunciation, and impairment closeout. Always verify the actual approved trim diagram, listing, and manufacturer reset procedure before testing or restoring the system. This section focuses on clean agent and inert gas protection for data centers. Engineered total flooding systems can minimize residue and speed recovery, but they only work as intended when the room, controls, and recovery process are managed as one system. The key point is that agent discharge is not the whole fire protection strategy. First, the hazard and agent basis must account for protected volume, design concentration, safety factors, temperature, altitude, and material compatibility. Detection and release controls then need approved coincidence or release criteria, pre-discharge alarms, time delays, manual release, abort functions, and lockout provisions. Enclosure integrity is equally important. Doors, floors, ceilings, leakage control, pressure relief, and hold time verification determine whether the agent can remain effective. The system also has to interface with HVAC and dampers, power isolation, security, voice alarms, the fire alarm control panel, building management systems, and cylinder pressure or weight supervision. Safe recovery includes evacuation, discharge confirmation, ventilation, atmosphere verification, controlled reentry, and recharge. Finally, energized equipment, hot components, and lithium battery propagation may reignite, so residual hazards require additional controls. FMDS 5 to 32 allows clean agent or hybrid approaches where appropriate, while identifying water-based protection as the broadest reliable standalone layer. This section focuses on the fire-water system and its connection to emergency response. The central idea is that water supply is a site resilience system, not simply a collection of pumps and tanks. Storage, drivers, controllers, testing arrangements, distribution, and brigade access all need to remain available during impairments and emergency conditions. The arrangement shown includes 2-cell water storage, jockey and main pumps, both electric and diesel, a ring main with test header and connections serving sprinklers, hydrants, and the FDC or Siamese connection. Design and acceptance should confirm usable volume and duration, suction conditions, dedicated pump controllers, churn, rated, and 150% test points, along with the ring main and FDC path. Operations are equally important. The normal valve lineup, fuel and battery readiness, hydrant and FDC access, pre-planned brigade information, and temporary supply arrangements must be understood before an incident occurs. Key evidence includes approved hydraulic calculations, pump curves, controller settings, tank and isolation logic, valve supervision, flow test data, alarm chronology, maintenance planning, and clearly tagged brigade connections. The cited interim FM guidance also identifies a 250 GPM hose allowance for 60 minutes, combined with the governing simultaneous demand and AHJ basis. This section focuses on generator and fuel system fire hazards. The key point is that the fire strategy must cover the entire fuel and equipment pathway, not just the generator enclosure. Fuel moves from the bulk tank through the transfer pump to the day tank and generator, creating several opportunities for loss of containment. Pressurized spray is especially hazardous because a failed hose, fitting, or pump can atomize fuel near an ignition source. A pool or spill fire presents a different challenge. Leaked fuel may travel beyond the equipment unless bunding, drainage, and isolation are effective. We also need to account for turbochargers, manifolds, exhaust components, ventilation, and other hot surfaces that can ignite fuel or nearby combustibles. Finally, control interaction matters. Fuel emergency shutdown, engine shutdown, valve closure, ventilation, and emergency power objectives must operate in an approved sequence. The protection checklist therefore includes appropriately selected detection, tested shutdown interfaces, a listed or engineered suppression system coordinated with the manufacturer and authority, and documented spill containment, environmental controls, response, and restoration procedures. This section focuses on electrical rooms, UPS equipment, and battery hazards. The central point is that protection must be matched to the chemistry and equipment involved, while also supporting service continuity and responder safety. A clean agent discharge by itself does not control lithium-ion thermal runaway or prevent propagation. For switchgear and UPS systems, the primary concerns are arc and thermal faults, insulation or cable failures, power electronics faults, and potentially high incident energy. The strategy combines thermography, smoke or heat detection, separation, EPMS alarms, and controlled isolation. VRLA and lead-acid batteries introduce different concerns, including hydrogen generation, thermal problems, electrolyte and corrosion issues, and dependence on reliable ventilation. Monitoring, gas detection where applicable, ventilation verification, spacing, and good housekeeping are key controls. Lithium-ion systems can experience cell thermal runaway, flammable or toxic gas release, propagation, deflagration, and long-duration reignition. Protection therefore requires coordinated battery management, off-gas and heat monitoring, ventilation and deflagration analysis, exposure cooling, and emergency response planning. The hazard analysis must also account for heat release, reignition, and firefighter tactics, not just the initial alarm or discharge. This section focuses on the interfaces between smoke control and HVAC, where the right strategy depends on the space being protected. In occupied egress areas, the priority is tenability, maintaining conditions that support safe evacuation. In a data hall, airflow, detection, and suppression must be coordinated much more carefully, because an exhaust response can affect both smoke movement and fire protection performance. The fire floor is controlled negative, while the floors above and below remain positive. On the fire floor, smoke extraction and dedicated makeup air operate together, with field verification of airflow, pressure, and door forces. Adjacent floors use supply or pressurization to protect egress and limit smoke migration. This is an illustrative relationship only. Actual zones, set points, and sequences must follow the approved analysis and authority acceptance. A key data hall caution is that smoke exhaust should not start from detection alone under FM guidance. Where local code requires automatic exhaust, it should be interlocked with sprinkler or water mist operation. Finally, the command architecture must prove fan, damper, pressure, and airflow status, while planning for failures, manual firefighter control, emergency power, and documented testing evidence. This section focuses on the integration boundaries between fire protection, MEP, security, ICT, and monitoring systems. The central point is that integration improves situational awareness only when responsibilities and operating rules are clearly defined. Integration must not replace local fire system authority or autonomy. The listed fire safety systems, including the fire alarm control panel, releasing panels, voice evacuation, fire pump controllers, and firefighter control systems, remain the primary safety functions. Other platforms provide supporting information. The BMS monitors HVAC, plant conditions, and fire mode status. The EPMS reports power status, breaker positions, and electrical events, while the DCM presents capacity and environmental information. Security operations add access control, doors, gates, CCTV, and incident response. Lift systems support recall, unlocking, and firefighter access. Approved remote alarm or cloud connections may extend visibility and preserve evidence, but they must be controlled. Across all these interfaces, the design should distinguish monitor-only points from commands. It should preserve local autonomy, maintain accurate time synchronization, and apply a cybersecurity management of change process. These boundaries determine what happens during normal operation, communication loss, or a conflicting command. This section focuses on how we turn requirements into evidence that can withstand review, approval, and future operation. The starting point is the adopted legal and HJ basis, because that authority controls final acceptance. From there, we identify the adopted codes and standards, including SNI, NFPA, or the I codes, while tracking insurer criteria separately when they add property loss resilience. Those requirements then become the project design basis, approved criteria, calculations, and defined interfaces. The important point is that infrastructure frameworks can inform availability, but they do not replace fire approval. The fire protection system still has to satisfy the applicable authority and adopted standards. The assurance chain continues through witness testing, commissioning, impairment control, and restoration. We need proof not only that the system works initially, but also that it can be safely managed when part of it is unavailable and reliably returned to service. Finally, every step should produce traceable, current, audit-ready records. That evidence connects the legal basis to the design to tested performance, and tested performance to dependable operation over the system lifecycle. This slide establishes the hierarchy we use when selecting and applying references for a data center fire protection system. The controlling principle is simple. Statutory acceptance comes first. Legal requirements, the authority having jurisdiction, and DAMCR determine the applicable regulations, permits, access, water supply, acceptance process, and emergency response obligations. Next, we apply the adopted fire and life safety standards, including the relevant SNI and FPA, or I code provisions, along with listed equipment, approved calculations, manufacturer instructions, and project specifications. Insurer engineering guidance, such as FM property loss prevention data sheets, then addresses property protection, impairment planning, reliability, and business interruption resilience. Data center frameworks, including ANSI/TIA, 942C, ISO/AC 22237, YEN 50600, and BICSI, help define infrastructure, redundancy, spaces, and operations. Certification and owner risk policies are valuable for assessing topology and availability, but they do not replace local fire code or AHJ approval. The practical rule is to use the edition adopted by the AHJ and written into the contract. A newer publication is not automatically mandatory, and any deviation needs documented approval and explicit risk acceptance. This standards matrix maps the primary references used across building, alarm, suppression, and lifecycle activities. It is not simply a list of codes. It connects each system to its design basis, installation requirements, acceptance criteria, and ongoing inspection and maintenance obligations. For building and life safety, the focus is occupancy, egress, fire areas, access, active systems, inspections, and emergency planning. IT equipment and telecommunications areas add requirements for construction, cabling, airflow, resilience, DC power, batteries, and telecom-specific hazards. Fire alarm and PAVA references address initiating devices, circuit survivability, notification, supervising stations, and ITM. Sprinkler, preaction, fire pump, standpipe, hydrant, and FDC references establish hydraulic demand, release logic, water supply, access, installation, and acceptance requirements. Water-based systems are then maintained through inspection, testing, deficiency management, impairment controls, and records. Clean agent and inert gas systems add agent calculations, enclosure integrity, pressure relief, release safety, and reentry controls. The key project output is the standards register, with adopted additions, clauses, design responses, drawing and specification references, reviewers, deviation status, and acceptance evidence. This standards map connects each major data center fire protection subject with its primary references and its practical training application. The important point is that no single standard governs the entire facility. Smoke control and HVAC fire mode draw on NFPA 90A and 92, adopted building and fire codes and local criteria, with attention to fans, dampers, emergency power, pressure, airflow, and firefighter controls. Water mist or hybrid systems require application-specific design, approved equipment, and acceptance testing. Emergency power, batteries, and energy storage systems bring in NFPA 110, NFPA 855, NFPA 70, UL standards, and manufacturer data. Commissioning and integrated testing then verify that systems work individually and together, including cause and effect sequences, failure modes, retesting, and handover. The broader infrastructure frameworks, such as ANSI/TIA, 942C and ISO/E22237, address resilience, topology, power, cooling, security, and operations. Uptime criteria and FM guidance add performance and loss prevention context. Certification does not replace legal fire protection approval by the authority having jurisdiction. Each framework validates its own criteria, while statutory acceptance remains a separate path. This slide organizes commissioning and integrated system testing into illustrative project gates, from design through handoff. The G0 design gate confirms the owner's project requirements, basis of design, standards matrix, fire strategy, and controls and electrical concept. G1 covers factory activities, including FAT, listed configuration, the software baseline, and witness records. G2 verifies installation quality, labeling, static checks, terminations, and fire stops. G3 is startup, where individual equipment is operated, calibrated, and configured. G4, or site acceptance testing, demonstrates functional performance, alarms, trip and release sequences, and hydraulic or agent performance. G5 is integrated system testing, using end-to-end scenarios that include failures, emergency power, and event chronology. Finally, G6 confirms handoff through as-builts, operations and maintenance materials, training, spares, and open-issue controls. The critical point is that G0 through G6 are illustrative project gates. NFPA 3 and NFPA 4 define the commissioning and integrated testing practices, not this numbering system. Evidence should cover normal operation, abnormal conditions, and restoration, with logs, trends, timestamps, test sheets, screenshots, defects, and retests retained. This slide translates NFPA 25 into a practical, asset-specific lifecycle program for data center water systems. The owner combines the adopted NFPA 25 edition, manufacturer instructions, and actual site conditions to define inspection, testing, maintenance, and deficiency workflows. The key is to connect every asset to both evidence and corrective action. For water storage, that means checking level, condition, heating, valves, corrosion, and the refill path, then documenting alarms, usable volume, and internal condition. Fire pumps and controllers require power, fuel, batteries, sensing lines, automatic and manual starts, flow performance, and alarm verification. Sprinkler and preaction systems focus on valve position, air or nitrogen, water flow, supervisory signals, trip and release performance, and restoration. The same logic applies to standpipes, hydrants, FDCs, backflow devices, pressure-reducing valves, and water mains. Inspect the physical condition, perform flow or pressure tests, and identify failures such as inaccessible connections, pressure mismatch, leaks, or unavailable loops. Finally, documentation must capture asset IDs, calibrated instruments, timestamp results, trends, open defects, and restoration status. Exact frequencies must come from the adopted edition, manufacturer guidance, system type, environment, and AHJ requirements. This section treats an impaired fire protection system as a managed risk condition, not a maintenance convenience. The process begins by identifying the affected zone, duration, scope, and initiating cause. Then a named owner authorizes the impairment, supported by a documented risk assessment. Required stakeholders are notified, including operations, security, the insurer, the AHJ or DAMCR, and others as applicable. Mitigation must be active, with measures such as a fire watch, temporary protection, restricted work or storage, and confirmed response readiness. Next, isolate the system through controlled valve, panel, or bypass actions, using tags and logs. Work and testing then proceed under an approved procedure, with repair, inspection, and functional proof. Restoration means returning valves to their normal lineup, clearing bypasses, confirming normal alarms, and completing end-to-end verification. Finally, close the impairment with evidence, notifications, lessons learned, and defect or management of change closure. The key rule is no undocumented or incomplete impairment. Prohibited practices include unapproved software disablement, untagged closed valves, expired fire watch, active test mode left behind, and treating repeated trouble alarms as normal. This slide presents an audit-ready evidence architecture for the data center fire protection system. The central idea is simple. Every requirement must trace through the entire lifecycle. That means connecting the code clause, owner criterion, insurer recommendation, or accepted deviation to a design response, the installed asset, documented performance proof, and ongoing lifecycle control. In practice, that evidence can include calculations and drawings, asset tags and configurations, FAT, SAT, or IST results, raw logs and trends, inspection and testing records, impairments, bypasses, defects, drills, management of change, training, and audits. The operational KPI dashboard then shows whether the system remains controlled over time. We want IDM completion at or above the site target, no overdue impairments, and deficiency aging trending downward. False or repeat alarms should also decline, with root causes and corrective actions documented. Pump curves need to remain within tolerance across churn, rated, and 150% conditions. Finally, any change must trigger a complete retest of cause and effect and interfaces. Missing or stale evidence is not merely a paperwork issue. It is an operational defect because it can conceal configuration and reliability risk. This applied scenario follows an incipient cable fault in a high airflow data hall, where a loose connection heats a cable or PDU without producing visible flame. The response is staged, and the exact outputs must always follow the approved cause and effect matrix. At T+1, aspirating smoke detection, or ASD, provides an early warning for the NOC or Fire Command Center to review the trend and location. By T+3, a pre-alarm prompts dispatch, camera verification, and any approved airflow action. If fire is confirmed at T+5, alarm and voice actions begin, the brigade is notified, and isolation is considered. The sequence then moves towards system ready, fire control through sprinkler operation, and escalating water flow and pump alarms, and finally recovery. Recovery includes safe isolation, atmosphere and heat verification, cleaning, recommissioning, and closing the management of change process. Throughout, the team should verify location, isolate safely, control airflow, and preserve evidence. The facilitator challenge is to identify 3 common mode failures and explain how each will be tested during integrated systems testing. This workshop turns the protection concept into a usable strategy register for one critical room. Select a space, such as Data Hall A, and document enough information to support design review, commissioning, operations, and audit. Start with the space function, credible initiating events, and consequences. For example, consider rack PDU faults, overheating connections, liquid cooling leaks, or temporary work. Then connect those events to smoke contamination, cooling shutdown, service loss, water migration, and access constraints. Next, record the barriers that prevent or limit the event. These may include rated boundaries, fire stops, material controls, electrical maintenance, hot work controls, and management of change. Define the detection approach, including air sampling locations, thresholds, and transport time criteria. Then capture the suppression basis, supervised points, and the selected wet, preaction, or agent system. The register must also show cause and effect interfaces, including doors, HVAC, power isolation, pumps, building and operational systems, and brigade notification. Finally, identify the IDM owner, impairment and restoration rules, and the location of supporting evidence. Every barrier needs an owner, interface, acceptance criterion, test method, and evidence location. That is what makes the workshop output auditable and actionable. This knowledge check is designed to connect the technical details to the decisions that matter in a real data center. I'll ask participants to explain why meeting minimum life safety code may still leave unacceptable business interruption risk, especially when the hazard, continuity needs, and protection strategy are not aligned. We'll also test the distinction between fire alarm inputs, supervisory inputs, and trouble conditions, because each represents a different type of information and response. Another key question is why double interlock preaction is not automatically the best choice for every data hall. The right answer depends on the specific hazard, system logic, and operating context, not simply on a preferred product or configuration. Participants should identify which platform is authoritative for fire event status and explain why that authority must be clear. They should also describe the evidence needed to prove that an impairment was safely restored. Finally, we'll reinforce that TIA 942 or uptime tier certification does not replace approval from the authority having jurisdiction. I'm looking for evidence-based reasoning throughout, rather than product preferences. This module closes with a practical view of what makes a data center fire protection strategy reliable. Start with scenarios, not room labels. Select the protection approach based on the hazard, airflow, enclosure, and consequence, so the design reflects how a fire could actually develop. Next, use defense in depth. Independent passive, active, and operational layers should continue to provide protection even when a credible failure occurs. Make the system logic deterministic as well. Every signal needs a defined priority, output, fail state, action, reset authority, and test method. Water reliability is equally essential. The supply, pumps, valves, and fire brigade interfaces must be accepted, maintained, and inspected through the appropriate NFPA 25 inspection, testing, and maintenance process. Authority roles also matter. Local law and the AHJ control, adopted standards govern, and insurer or framework criteria can add resilience. Finally, treat evidence as an operating system, not paperwork. Drawings, calculations, testing records, maintenance, impairments, and management of change all need clear ownership. The module deliverables bring this together through protected space and boundary maps, a standards matrix, scenario and barrier registers, and an evidence owner map. This slide consolidates the primary references used for the data center fire protection system. The key point is that these documents must be applied using the adopted edition, with project-specific confirmation from the AHJ or DAMCR, including local interpretations, amendments, listings, and contractual requirements. The Indonesian legal basis is provided by Permen PUPR 26/PRT/M/2008 and PP 16/2021. FMDS 5-32 addresses data centers, with the additions and interim timing identified on the slide. The NFPA references then cover the major technical disciplines. NFPA 75 for information technology equipment, NFPA 76 for telecommunications facilities, and NFPA 72 for fire alarm and signaling. NFPA 13 addresses sprinkler installation, NFPA 20 covers stationary fire pumps, and NFPA 25 provides inspection, testing, and maintenance requirements for water-based systems. For specialized protection, NFPA 2001 covers clean agent systems, while NFPA 92 addresses smoke control. Finally, NFPA 3 and NFPA 4 support commissioning and integrated testing of fire protection and life safety systems. Together, these references establish the technical, legal, and verification framework for the project. This slide brings together the primary references supporting the data center fire protection concepts in this module. The sources span several areas: energy storage installation through NFPA 855, building and fire protection requirements through the 2024 International Building and Fire Codes, and data center infrastructure through ANSI/TIA 942C and ISO/C22237. I've also included the Uptime Institute Tier Framework, ISO/IEC guidance on security systems, FM property loss prevention data sheets, and official access pages for NFPA and TIA materials. For an Indonesian context, the list points to the BSN catalog, including the SNI 3989 series and SNI 6570. The most important qualification is that these references are supporting resources, not substitutes for enforceable requirements. The legally adopted building and fire codes, together with acceptance by the authority having jurisdiction, always govern the final design and approval. Copyrighted standards are identified by title and official access page. This deck summarizes engineering concepts, rather than reproducing controlled standard text. This glossary brings together the abbreviations used throughout the Data Center Fire Protection Masterclass. The key is understanding how these terms connect across disciplines. Detection terms include ASD, HSSD, and VWFD, while control and response terms include FACP, FCC, FDC, and FFCP or FSCS. Operational coordination relies on systems such as BMS, DCM, EPMS, and NOC or SOC. Project delivery terms include CX, IST, IDM, MOC, OPR, BOD, and SAT. Use these definitions as a quick reference when reviewing the module's systems, processes, and responsibilities.